Well, thanks so much for having me. I really appreciate the opportunity to come and speak. A couple of words of background about myself. I've actually been with NREL on 3 different occasions for a cumulative a little bit more than 20 years at this point. I first went as a graduate student when it was CRES, and did my graduate work in photovoltaic materials and devices, and I went to School of Mines actually as a postdoc, came back as a regular NREL employee, still CRES actually, but then turned into NREL in 1992. I went out and worked in the private sector for 7 or 8 years at a PV startup, and went back to the lab in 2002 on a 6-month temporary assignment while I figured out what else I was going to do, and now I'm still here. I've been since August of 2002. Because I realized after being out in a couple of different places is every place has good things and bad things about it, and on balance, NREL is actually an excellent place to work. So I do encourage everybody who is looking around. And we actually do have a great diversity of backgrounds and skill sets needed at the lab. So if almost everything I heard actually. I can think of positions that are suitable at NREL. So take a look. And this, the talk I'm going to do tonight is just talking a little bit about what's going on in the wind and solar markets. Toward the end, we'll talk a little bit about some of the implications for the power system with the markets booming the way they are, and also talk a little bit about economic impact nationally and in Colorado. But I tell you, I first started doing work in the lab on PV materials in 1988. And the global manufacturing capacity in PV in 1988 was about 10 megawatts. 10 megawatts. There's one plant in China right now that is about 2.5 gigawatts, a single plant. And so things have changed. They changed just a little bit, but I tell you, what's happening now is the period that those of us who were kind of starting in the late 80s, early 90s kind of time frame, the period we all kind of were hoping would happen, but never really genuinely thought would, but it actually is. And I'm going to hopefully demonstrate to you tonight that it's a very exciting and dynamic time in the wind and solar industries. I'm going to just give a quick overview of global trends in renewables. A lot happening actually all over the world, which benefits the U.S., but the U.S. is certainly a leader, as I'll show in the slides. And I'll talk a little bit about wind and solar markets, a little bit in the market segments and what's going on in the technologies in the second part, do those kind of separate, and then at the end, talk a little bit about how the power sector is undergoing a transformation right now, thanks in large part to cheaper wind and solar, but also very abundant and cheap natural gas, and then go into the economics a little bit. So again, starting out with the global picture, going through these sub-bullets for wind and solar, each separately in the same order, a little bit about the power system, a little bit about what's happening in jobs in this sector. And so I set it up like this, so I always gray out everything I'm not talking about. So this is installed renewable energy capacity, including conventional hydro, globally. The total global electricity generation capacity is about 5,900 gigawatts, so 5.9 terawatts. So there's a lot of electricity that's produced every year. The U.S. accounts for about 1.1 gigawatts of that, so we have the biggest system by far. It's actually broken into 3 parts, but the continental U.S. has about 1.1 terawatts of electricity generating capacity. And renewables now are all the way up to about 30% overall, including conventional hydro. Excluding conventional hydro, we're all the way up to 12.5%. So this is dramatically different. This only goes back to 2005. And it's a little bit of a tricky time of year because we're just now starting to get good numbers for 16. So some numbers, if I have numbers for 16, I'll show those, and hopefully everything is labeled well. But a lot of stuff ends in 15 because that's the last calendar year for which we have really solid numbers. But one of the interesting things you see in this plot going back from 2005 is that The bottom three parts of the bar, conventional hydro, the big blue one, still the dominant, and the green and the red, geothermal and biomass, they don't change a huge amount. There's been conventional hydro added, as you can see, but the real gains you see are in the blue and the orange, and that's wind and solar. And you see getting out here in 15, it's approaching 50% of the overall. And 16 we know was an excellent year for wind and solar both. And so once the 16 numbers get cemented, I'll be surprised if we don't see wind and solar accounting for about half of all global renewables installed. So just a map. Some of these graphs you can find in a publicly available presentation on the NREL website called the Renewable Energy Data Book. And so this just shows the top 5 countries for each of the major renewable generating technologies: hydro, PV, CSP, concentrated solar power, geothermal, wind, and biomass. And you can see the U.S. Is doing very well in all of them. We're definitely one of the world leaders, but China has overtaken, you can see, in a number of the categories, wind and solar especially, and hydropower. So we'll walk through the technologies a little bit, and I can't help but anytime I do one of these presentations, I mean, I, for one, always, and I think this is a friendly crowd. I love looking at pictures of technology. So I try to find some of the impressive ones. This is the wind farm in China, up in the northern part of the Gobi Desert in China. That's going to be the biggest one in the world. It's currently, I think it actually currently is the biggest one, but it's growing. It's currently at 8 gigawatts of capacity, and going to 20. And so that's an enormous wind farm. Several things about China is that once they have made the decision in the central government to do something, they really do it. I mean, they don't hesitate. They drive ahead, and you know that's really been a double-edged thing for us, especially in solar. It's made it very hard for American manufacturers to be competitive in solar. But the flip side, and it depends on where your interests lie, whether it's a good thing or a bad thing. But the flip side is that it's caused a huge proliferation, of PV around the world. I mean, because they drove the prices down so dramatically, like I'll show in a moment. Offshore wind is a major and growing market segment for wind, and these are just a couple of really cool pictures in Europe. Europe has really driven the offshore wind market. In fact, the U.S. only in November of 2016 commissioned its first offshore wind plant off of Block Island, Rhode Island. Small wind farm, only about 30 megawatts, as compared to these. You see this 160 down here, 144 up here. And then we have a really strong position, though, in onshore wind. And in fact, eastern Colorado is in the U.S. wind belt, and I have a couple nice shots here from big Colorado plants. The Pete's wind farm is the biggest one in Colorado, up in the north by the Nebraska border, 575 megawatts. Cedar Creek is nearly as big at 550 megawatts. So these are really large wind farms, and I'll go into a little more detail about specifically what all's going on in Colorado. I want to talk a little bit about the technology, though, because it's so darn impressive. This is from the National Wind Technology Center that most of you have probably seen going on 93. And these are the shot of the three of the big ones that are there. We have a fourth one now that's not in the frame. But as you're driving by, unless you've had the chance to go stand underneath one or even go up at a tower, it's really difficult to appreciate or get the right perspective of the size of these things. One of the reasons I included this is that you can see somebody on top of the Alstom machine right there. I mean, these are enormous machines. This is about as big a land-based machine as exists in the market now. It's a little over 3 megawatts. The single wind machine is, and there are a number of reasons for that. But the principal reason this is as big as, about as big as we get on land, is that our transportation infrastructure can no longer accommodate the size of the pieces that need to be shipped to the site. One of the really interesting R&D areas that we've got going on at NREL is looking at ways through new technologies like 3D printing of how to do on-site manufacture. And or potentially how to do segmented blades, so you can ship the blades to the site and assemble them, do the final assembly on site. But for right now, around 3 megawatts and a hub height of about 100 to 120 meters is about as big as you get on land. But offshore, you can go much bigger, because you can put the factories at a shipping port and load everything onto giant barges in single pieces and ship them out. So this is an example of a commercially available machine from Vestas, who is the big manufacturer in Colorado for our land-based wind here in Colorado. This is a 7 megawatt machine, and you can see the size of it is really stunning. It's that's a 747 there, gets compared to everything big. But just look at one of the blades. London double-decker buses, 9 of them make up the length, and you can, and the end of it is so big. The diameter is so big you could actually drive one of them into it. So these are impressive machines, and a number of advantages for offshore, though. In addition to being able to build them bigger, you can increase. You can if the sweep is much larger, you can put the hub height higher, and the winds tend to be steadier and more predictable the higher the hub height gets. So the capacity factor of and the predictability of the output of the machines all gets much better. So a little bit about global wind markets, where everything is happening in wind specifically. Many of the same countries that we saw in the overall renewable map are also highlighted here. But you can see China here is, in the last 2 years, has just sort of blown by everybody, so to speak. And this is, again, though, 2015 data, and we have our current data, though. We had it was a great year in the U.S. for wind, about I think it's 8.2 gigawatts installed in 2016, so we're up in the low 80s now. But even with a really good year like that, where we didn't even come close to catching up with China. But you see, it falls off pretty quickly. Germany and many of these wind farms in Europe, Germany and the UK, are mostly offshore. And so for Colorado specifically, I do this in the context of the entire U.S. You can see a lot of numbers up here, but Colorado currently has just a little over 3 gigawatts installed, which is really significant because the Colorado system, the power system, isn't enormous. We have the annual average right now at that capacity is about 16 to 18% of Colorado's megawatt hours consumed come from wind energy. So a pretty significant amount. I mean, we're really getting up there, and that's an annual average. That sort of 16, 17% numbers over the course of the year. That's what it amounts to. But that can lead to some very high instantaneous penetrations. In fact, XL is despite some other issues they may have, they have been really in the forefront of learning how to operate power systems with high penetrations of wind. They've managed the system with instantaneous penetrations, and by instantaneous in the power sector, I mean over the course of an hour. In fact, over the course of 4 hours, they had about 54% penetration. So 54% of the power on the Colorado system was being supplied by wind at that particular time. And that was just I think that was this past October. Those really challenging times for the power folks tend to happen on the shoulder seasons, spring and fall, when the temperatures are down a bit, but the wind and sun are up. And So you can see that we rank 10th in the country in terms of installed capacity. We've got 76 megawatts under construction right now, with another 600 that are in an advanced stage of development. The Rush wind farm that Xcel is actually building, I think that's the one they're building and owning on their own. The first one they're going to do that. They get most of their wind through various other kinds of power purchase arrangements. But an interesting study my group did a couple years ago was we did a multi-step deduction to try to determine what the technical potential was for renewable generation in the U.S. and state by state. And what I mean by technical potential is you take the entire resource and you begin to eliminate areas where it's not feasible to build out that particular kind of generating capacity. So for wind, you can't build it very easily in the mountains. It becomes completely uneconomic, even though some of the best wind resources along ridges up there. So you eliminate those. You eliminate downtown Denver, and downtown Colorado Springs, and national parks and state parks. And so finally you get down to only those areas where you actually can physically put the plant. And then we look at what the resource is, and we have very detailed resource data sets. We look at the resource and then say, okay, if everything were built out where you could build it out, this is how much power we would have. And the numbers are actually just ridiculously large. 387 gigawatts is the technical potential we determine for wind in Colorado alone. So a full third or greater than a third of the entire capacity of the U.S. system, the nameplate capacity of the U.S. system, just from wind, just in Colorado. So the renewable energy potentials, and you see that in most of the states in the wind belt, you get kind of similar numbers. The only place where the numbers really fall off, as you can see, where no wind is currently being built, is the southeast. There's just not a great resource there, although some of our recent analysis suggests that if we can get land-based hub heights up to 120 meters, there's a much greater technical potential in the southeast. So just a quick snapshot. This is pretty familiar probably to many, the wind resource map for Colorado. And the darker the color, the dark blues and reds and purples are the best wind. And this, you can see here where all the wind farms are, down here in the good wind area, and up here along the Wyoming and Nebraska borders, some of the best wind in the country. And the gears here show where there are major manufacturing facilities in Colorado. And I mean, we're a great example of what renewable energy can mean to local economic development, not only, especially for wind, because it's quite expensive to ship those large heavy parts. Vestas, a company from Europe, built manufacturing plants here, and it confuses some of the political arguments about globalization or not, because this is a European company that's come and set up shop in a really significant way in Colorado and created a lot of really great local jobs. But beyond that, I mean, legitimately, they can move those plants wherever they want. But once the generating plants are built, those jobs don't go anywhere, and the wind industry has resulted in a pretty significant revitalization of a number of rural areas in Colorado and all throughout the Midwest, especially because those machines need attention. They require operation and maintenance, and there are a lot of big moving parts, so they don't just run forever by themselves. So lots of good jobs being created in areas that have seen jobs fleeing now for a few decades out of the agricultural communities because of the mechanization of agriculture. So a lot of words and numbers here, and this will be available for everybody. And if I go through something too quickly, and because I might start running out of time, feel free to look it back up or contact me and to discuss later. But I've actually already hit some of these numbers just through the course of talking about it a little bit. But some of the environmental benefits are really substantial, and I point out to one. Annual water consumption savings in Colorado from wind alone, 4.4 billion gallons. I mean, this is something that's only now really starting to get a lot of attention, especially in the analytic community, of trying to better appreciate the interplay between the electricity system and the water system.
Why is that? How does it save water?
Most conventional generators consume a lot of water. They have to, they use steam to drive turbines, and they have to cool. So it's there's a lot of withdrawal and consumption from conventional plants. And the wind actually requires zero. PV and CSP require some. Concentrated solar power usually drives a conventional turbine, so it's not a huge water saver. It's less than like a coal plant or even a gas plant. But PV uses a little bit, especially in the desert Southwest. It's you wash them every now and then if it doesn't rain very much and there's a big dust buildup. So this is, we're beginning to learn more and more about that relationship between water and energy, because not only does it take a lot of water to produce energy, especially conventionally, but water itself in pumping in either municipal use, industrial use, agricultural use consumes a lot of electricity. So you have to generate a lot of electricity just to move water around. So there's a lot of really interesting interplay there, and we're trying to understand better how we can recognize and realize efficiencies in treating them as an interacting system. So this is for the U.S., the cumulative wind capacity going back to 1980. So you can see a lot has started to happen in the 2000s. This is when things have really gotten exciting. Those are the blue bars. And as I pointed out already once, we had 8,700 megawatts in 2016, giving us a total in the U.S. of about 81,312. I've seen some numbers that were up closer to 83, so people are still trying to get all the numbers right. And the orange line, not coincidentally, is the cost of wind on the right axis over there in cents per kilowatt hour. So you can see really dramatic reductions since the 80s. And I'll show a couple more slides about cost here in a second. So this is, we've started, 3 years ago, we started producing something called the Annual Technology Baseline. The EIA, the Energy Information Administration in the U.S. Department of Energy, has had the historic role of tracking, a lot of times backcasting, looking at energy cost and doing some forecasting as well through the annual energy outlook. But they've never really focused very intently on renewables. They're changing. They're really, because it's becoming a much more significant industry. They've started to do a little bit better, but we thought that for our analysis, we needed to all agree on a set of numbers that we use in all of our analyses. And so every analyst, when they start a study, is not coming up with their own set of numbers. So these numbers come from the Annual Technology Baseline that's available also online. You can download at no cost. And these are hard to read, I know, so I'm gonna draw a couple lines, and this is the lowest cost land-based wind numbers that we were able to find. About 5 cents a kilowatt hour, just slightly under $50 a megawatt hour, same thing. And you can see, though, that for land-based wind, the range is very large, and that can be dependent on a lot of things. Where the plant was built, the cost of labor in that location, but the big driver is what the wind resource is. This is very likely maybe a plant up along the Colorado-Wyoming border, or maybe in Wyoming. Wyoming has some of the best wind in the country. And yes, go ahead.
Is this with the subsidies removed?
This is without subsidies, correct, yes. But I draw the red line from the lowest cost wind, and we go across here just because you can't read it. There's land-based wind, offshore, utility PV, commercial PV, residential, concentrating solar power, geothermal, hydropower, and then the conventionals over here, coal CCS, coal combined cycle, gas with carbon capture, nuclear, and biopower. But you can see the lowest cost wind only intersects with combined cycle gas. It's the best cost wind is cheaper than everything else. So this is where we've come, and this is why everything is changing and changing really rapidly. But you can see if you build it in not such a great location, you draw that line across there, it's more expensive than almost anything. So there's a big variation. So it's very, very site dependent and depends on a lot of factors, what the balance of the generation mix of the utility is, what the utility rates are, a lot of things like that go into a decision as to whether or not to build. So just because I have this chart up here now, I'll come back to solar costs later, but if I look at the cheapest solar utility scale PV, that's right here, it's cheaper than almost everything else, and this has been the really radical change in the last 2 years, what's happened to the cost of PV. It's exciting, it's really remarkable, and it really portends a very different power system in 20 years than we have today. So a bunch of confusing lines here, but these are costs for wind in a little more detail. These are actually power purchase agreements, so these do include the subsidies because what somebody enters into a power purchase agreement in, that subsidy is baked in some way. But the purple line, I'll get you to focus on that one. This also shows you too a little bit about the difference the regions make and the quality of the wind, what the quality of the wind resource can do to the prices. But the purple one is in the interior, which is the wind belt, kind of Minnesota, North Dakota, on down to North Texas. And you can see that in 2016, this is only the two power purchase agreements were in this so far. That's all we have in the inventory of these contracts representing 200 megawatts. But the cost was all the way down with the subsidies at less than 2 cents a kilowatt hour. That was in Colorado. At least one of them was in Colorado. There are probably others. So less than 2 cents. I mean, that's really cheap. Your utility bill, as most of you likely know, being interested in energy, is around 10 cents a kilowatt hour is what you pay.
Sorry, just on the combined cycle, it's so important what you assume for natural gas costs and
Yes.
because we don't know where we're going with that.
So the combined cycle gas cost here, this is actually, we pull the conventional generators from the EIA data. The Energy Information Administration data. This is what it represents, but this is in 2015. So these were known gas prices. As we go out projecting, we go out to 2030 in the annual technology baseline, projecting costs into the future. That's when the bars get much bigger for everything, because exactly what you said, we don't know what the price of natural gas is going to be. Most people are, in their analyses, including the EIA, including NREL, are continuing to use natural gas prices out in the 10-year horizon in the $4 to $6 range. Most people expect, unless there's something radically changes with hydraulic fracturing, there's going to be a pretty significant abundance of natural gas in the 10-year time horizon.
Per million BTU, right?
Pardon?
Per million BTU, 4 to 6.
Yes, right. Sorry. But very cheap power purchase agreements here. But you can see as you get the green line, for example, is in the west. So over in California, Washington, and Oregon. There's some great offshore potential over there, but not cost effective yet. There's those would all be deep water platforms, and those aren't very commercialized yet. Yes, sir.
I know the Scandinavians and the English are working on floating platforms.
Yeah.
And that are not structurally attached to Earth, and that is what California and Mexico needs in a bad way.
No, that's right. It's right.
Is it the Vestas and the GE, the big players that are doing the
No, they're all the big players are working on those solutions. You can imagine though the engineering challenges associated with that. If you have if you have literally a flexible blade the length of 9 buses, and when the wind's blowing,
I think they'll put the 7 megawatters out floating, will they?
no, yeah, they're working on the big ones. But you know, if you've got the tip that's already bending toward the tower in a strong wind, but then if you also put into the mix the motion of the tower, because it's not anchored to the bottom. Huge engineering challenges. People are doing it. They are prototypes, but they're not anywhere close to cost effective yet. In fact, offshore wind in general tends to still be more expensive than land-based wind.
You're going to have to cut off the questions.
I'm sorry.
Mitsubishi Heavy Industries and Vestas have a joint venture working on it.
Mitsubishi and Vestas, yeah. So, oh yes, about you can just see the variation and the variation in region and the cost of wind, and you can see the bars, which are the national averages, track pretty closely to that interior line because that's where most of the wind is being installed. Okay, now we'll step through some of the same slides for solar, and so I think you all are probably very familiar with the markets for solar. People in the industry tend to break them down into three major segments: residential, and just some nice pictures here of the different ways residential get installed, ground-based, retrofit, rooftop, and then I used to have an old picture of a house in Florida with PV shingles, an old technology, but this is a shot of the new Tesla. Our Solar City integrated roof tile. That's been a long time coming. I mean, and it remains to be seen whether that's going to be a successful commercial product. There are a number of really significant engineering challenges, as it turns out. A lot around thermal management. PV doesn't like to be hot. The efficiency deteriorates pretty significantly with rising temperature, or it can. And so in this, for example, you've got this big air gap underneath the panel, so heat gets removed by convection that way. But when they're integrated, there's not much of a place for heat to go. So I haven't seen one of these systems, one of the new Solar City systems yet, to see how they're dealing with that. But I would think at this point I'm hard pressed to doubt Elon Musk. I mean, he's shown that he can do a lot of stuff that goes against conventional wisdom. So residential is usually between a kilowatt and 10 kilowatts in capacity. And here's a nice shot of IKEA. They've been really progressive in installing PV, a commercial type. A lot of times you'll see it referred to in the trade press or in other literature as non-residential instead of commercial, because not only does this include these kind of big box type retailers and warehouses, usually between I don't know, say 50 kilowatts and 10 megawatts, depending on the roof, are the commercial system. But these also include places like hospitals and schools and universities, and that's why it's sort of shifting to the non-residential moniker. And then utility scale, and this is, and in terms of cost, residential tends to be the most expensive per installed kilowatt, commercial next most expensive, and then utility the cheapest. And this one's right here in Colorado. Maybe you've been down to see this. This is just outside of the town of Mosca in the San Luis Valley. And if you're looking back, I don't know if they're visible in this. These might be snow-covered sand dunes back here. It's Great Sand Dunes National Monument. These are the Sangre de Cristos. And this is where XL had the first plant built in Colorado after the portfolio standard passed. And I have a little bit of an affinity for this plant because it's a little bit of an interesting story, is that we had, this was probably about 2004. I can't remember when exactly. Does anybody remember when the portfolio standard passed? 2004. So shortly after it passed, a group from Excel contacted us, and they came over and to meet with us to start talking about how they might begin addressing their commitments under the solar portion of the portfolio standard. And so they came in the conference room, and they all joked that they were the ones at the utility that had drawn the short straws, and they were forced to come out and talk to NREL. And so that was actually funny at the time. It was, but I formed some really nice relationships there because the people that they did assign it were really committed to it. And I did the analysis actually for them that identified this as a site to pursue, and it was a surprise to me. I mean, I learned in doing that analysis. I was doing projected outputs for plants all around the state, and realized that the valley down there is one of the premier places in the country for photovoltaics. It's because it's very sunny. About 320 sunny days a year down there, but it's also at a high elevation, about 8,000 feet, so the temperature stays cool. And so the output per rated kilowatt is higher than a system in Albuquerque, higher than a system in Phoenix. So it's a great place. Unfortunately, there's no transmission out of there to get it over here to the load, so that's a whole nother topic of conversation. But I remember the meeting we had where I presented the results, and the next week they had bought land. So they were ready to move once they got the information. And so that's actually, they started out with about 8 megawatts, and I think that's up to about 30 right now, the entire complex, 30 megawatts. And this is only a portion of the 8 megawatt one, so they're really impressive. I mean, they're very large. A big number of panels. So, and I also can't help but show the biggest ones in the world, both of the biggest ones in the world, although there's one in construction in China. Not surprisingly, that's going to be much bigger than anything else. This is in California. You can see where the red dot is there. This is called Solar Star. This is SunPower single crystalline silicon modules, 579 watts, megawatts AC, so that's up close to 800 megawatts DC. And it's 1.7 million panels, 1.7 million panels that cover 5 square miles. So a big system. And then here's a next era energy system. These are cadmium telluride panels, so a thin film technology from First Solar, and it's about 550 megawatts AC, so again up close to 800 megawatts DC, and 8.8 million panels, 8.8 million panels in that system. You can see again down here in the California desert. I've seen this one from a plane flying to San Diego one time. That was pretty cool. So the global solar market, again, you can see China in the lead with 43.5 gigawatts of installed capacity. We're actually, I have the 16 numbers now for the U.S. A couple of caveats about this actually. This 27.4 number does not include residential rooftop. It's only the big systems. And so we were actually a little bit higher than this even in 2015, but in 2016 we had the best year ever in the U.S., and now we're up over 40 gigawatts of installed capacity. These are the states where most of the action is happening. Colorado, a leader here as well, and the desert Southwest, as you might expect, and Texas also playing prominently. But there's an interesting little lesson, I feel like, from this graph. You can see that this is not the solar hotspot in the country up here, but it's a demonstration of the importance of two different factors: policy, state policy, and utility rates. These are some of the highest utility rates in the country, so PV becomes competitive much sooner than where we have really low utility rates. And Colorado is among the low utility rate states. But New Jersey and New York and Massachusetts and North Carolina too, I'm a North Carolina native. The sun doesn't shine there nearly as much as it does here. But they were very progressive in their renewable energy policies, and it caused a lot of deployment. It's also the case, there's no better demonstration than Germany. It was only in 2015 did Germany get surpassed by China as having the most installed capacity. Germany was became very aggressive in their policies in the early 2000s, and they implemented a feed-in tariff so that you got paid from the government for every kilowatt hour you put on the grid, and it caused this enormous boom in Germany of photovoltaic deployment. But the interesting thing about the solar resource in Germany is that it's equivalent to Seattle. It's equivalent to northern Maine, the entire country. I mean, the solar resource in Germany is really low quality. But if the right policies are in place, and the beautiful thing about solar is that even though a lot less sun shines there, they still produce a lot of solar energy in Germany. I mean, the sun is ubiquitous, and the panels generate. They don't require either on or off. They linearly output based on the irradiation. So here's the latest. A little bit different this graph is than the wind graph. The wind graph showed cumulative deployment going back to 1980. I start this much sooner. Back to 2010, but and so these are actual annual numbers. These are not cumulative numbers, the bars, annual deployment. But the interesting thing about the 2010 bar is that this is a cumulative bar. This represents everything deployed from 2009 back. That's everything. And then look what happened in 11, 12, 13, 14, 15, 16. 16, we had over 14 gigawatts installed. We were just barely at a gigawatt cumulative in 2010. So this is really dramatic, really exciting stuff. And again, not coincidentally, they're very much interrelated. The price has fallen dramatically, causing deployment to increase, and the more the deployments increase, which has been the point of so many policies, if everybody thought if we can get deployment increased, there's a learning curve that gets experienced in most industries in manufacturing large quantities of things. You're able to do it better, more efficiently, supply chains get matured, and you drive the cost down. So I've got this utility cost at about $1.20 a watt. We already know from the first quarter of 2017 some of the numbers that we're hearing about. There are some systems going in the U.S. For less than $1 a watt, which $1 a watt's been a big threshold for us. It was the Department of Energy Solar Program's 2020 target. So we're ahead of schedule in a pretty significant way here.
I missed that. Was that an installed cost or?
Installed cost, yes. Installed cost. And it's because the modules, I mean, everything is getting cheaper. All of the balance of systems componentry is getting cheaper. Experience in installation and installation techniques and designs are getting better and cheaper. But the module has driven everything. In the first quarter of 2017, you can buy crystalline silicon first tier, as we call them, first tier crystalline silicon modules for 35 cents a watt. 35 cents. And so that's stunning to me. I mean, when I started, my graduate work was on copper indium diselenide, which is a technology that has really only been deployed in Japan. There's only one major manufacturer of that. But when in the late 80s and early 90s, our target was, we thought thin films would, all of our analysis was suggesting that thin films would be the long-term winner in the market because you could use so much less material and they were so much more manufacturable. But for a very a large number of interconnected reasons, that never happened. Silicon kept getting better and better and cheaper to manufacture. But our target back when I was a graduate student was 50 cents a watt for the thin films. This is 35 cents a watt now for crystalline silicon. So, and it's meant a really robust industry for Colorado. This is where I come down on the side. I would love it if we were still manufacturing all those panels in the U.S. Back when I was a graduate student, we were the leaders in manufacturing because most of the technology had been invented here. Even though we're not manufacturing panels, there's been a great industry emerge here in Colorado and many other parts of the U.S. throughout the rest of the supply chain. I mean, there are 300,000 people that work in solar now in the U.S., even though we're a minor player in the manufacture of the panels. And, I'll take that because not only do we have 300,000 people working in solar, way more than working in the coal industry, but we're getting all this solar in the ground. And so all this clean energy is being produced as a result. It'd been nice if it had happened a different way. Like I said, it would be great if we were doing all the manufacturing, and I wish that we were, and we're constantly looking for ways to look for competitive angles for U.S. to get back in more manufacturing. In fact, I'm going a little far afield here, but one of the analyses that our group did is we did a very detailed supply chain analysis of the manufacture of a crystalline silicon panel and compared all those cost elements in the U.S. to the cost elements in China to see, was there a fundamental reason that we could not compete with Chinese manufacturing here in the U.S.? The most interesting thing to come out of that, it got a lot of attention at the time, was that we found that labor, the cost of labor, was actually a secondary factor, was not the driver for making the Chinese able to build panels much more cheaply. The two main factors is that when they decided to do it, they did it in a really big way, and when they did it, they much more rapidly matured the entire supply chain from raw silicon to panels than was happening here in the U.S. So by maturing their supply chain very quickly, they drove the cost out of it much more quickly than we ever did. And the other thing, which is, I don't know if we would ever actually, this particular element we could compete with, they had access to a lot of low-cost capital that American companies didn't necessarily have access to. The technical potential in Colorado for solar, I have that number somewhere. Oh yeah, 4,500 gigawatts in Colorado all by itself, 4 times the size of the U.S. system.
At that time, I think they stated that what we needed to run the state was 13 gigawatts.
Yeah, it's our system. Let's see if trying to remember the overall size of the system because it's broken up into several utilities. XL's one, and we have several co-ops, and then there's the West Slope utilities, and I can't remember the size of the entire system off the top of my head, but that's in the range. That's certainly in the range. Yeah. So the thing is, one of the things that I've been kind of glossing over, and I'm probably not as careful about it as I need to be, is that the capacity, I talk mostly in terms in this talk of nameplate capacity. And that's how much energy that could be generated if there was continuous fuel. So if I had let's just say if I had a 10 megawatt PV system, and the sun, I had a way to have the sun shine on it 24 hours a day for the entire year, it would have 100% capacity factor, and it would continuously produce 10 megawatts. Every hour, it would produce 10 megawatt hours of energy. But it doesn't work that way. The sun doesn't shine all the time, and so PV systems in the best locations in the U.S., fixed PV systems will only have a capacity factor in the low 20s, so around 20 to 21, 22. The systems that are tracked can have up to 24 or 25% capacity factor. So if I have a 10 megawatt system then that has a 25% capacity factor, over the course of that year, I only get out 2,500 megawatts effective. So That's an important thing. So if wind has a much better capacity factor in the wind belt, usually about 40%. So over the course of the year, you'll realize 40% of the nameplate capacity. And so that's why it's a little difficult to translate megawatts into how much actual energy you need to supply the state. And as a point of comparison, nuclear plants have about a 90% capacity factor. Coal plants in the high 80s. Storage is actually, as you're going to discover in May, is a whole nother vast topic that's really very, very interesting and not widely understood. There are a large number of applications for storage in the grid, and a lot of different technologies that can perhaps be best applied to those different applications. But in the end, though, still in most utility markets, there is no market with which you can monetize the value of that storage. So that's one of the big problems to getting storage in the system. So these are just a couple solar maps of Colorado, but you can see down here that area where the big XL plants are in the valley is the best part of the state. So this is the picture for Colorado for solar deployment. And again, I have it broken down into the 3 market segments. But you can see these are annual again, not cumulative. So 2016 was a huge year. Mostly you can see in the bar from here up is utility scale systems.
What happened in 13, 14?
Mostly no utility systems went in 13 and 14. The reason 16 was such a big year is that a lot of projects got in the pipeline when everybody thought the tax credit was going to expire at the end of 16. So it ended up getting extended. Congress extended it in December of 15. But a lot of those projects, because it takes a year to 2 years to do the big projects, a lot of those got in the pipeline so they could get commissioned by the end of the year and take advantage of the tax credit. They extended the tax credit now to 2020. A couple of key points off of this slide is that in Colorado we have over 6,000 people employed in solar, 382 megawatts. I think I've already hit that number. Prices in Colorado have dropped 64% in the last 5 years. So I've already hit most of this, but this is over here the utility cost. And you can see this dramatic drop. They were changing so quickly, we started keeping track by quarter. It was too much happening in a year. But you can see in Q1 of 16, and this comes from a bottom-up cost model that not reported prices from industry, but a bottom-up cost model that NREL has developed. And this is the number now that's coming in at less than $1 only 1 year later. Power purchase agreement costs, you can go back and look at this one. Again, you can see a wide range in every case due to a number of factors, what region it's going in, what the solar resource is. So a couple of notes about the power system. So this is the U.S. power system. These are the generating technologies represented by the different color lines. Coal is the gray line at the top. We always have coal as the gray line. But you can see here in 2005, look what happens. And so I draw your attention really to 3 lines that are the ones changing the most. Coal, the blue line is natural gas generation, and the green line, coming on strong, is the renewables line. And so for the first time in 2015, gas generation surpassed coal, and in the modern era anyway. And so this is if you care about climate change and you care about air quality, this is a really good graph. Things are changing quickly and for the better.
Can you say the other lines?
Yes. Sorry, it's not easy to read. This yellowish line, the orange line, is nuclear. So you can see in kind of maxed out in the mid-90s. To about 20% of our overall generation, nuclear still is. Even though France has the reputation of being sort of the nuclear state, and they do get the vast majority of their energy from nuclear. The U.S. operates the largest nuclear fleet in the world, about 101 operating plants still. This darker blue line is hydro, pretty much flat over the course of this period. This line here is petroleum. So in the 70s and on up to around 1980, petroleum use for electricity generation, burning petroleum, had increased, but it has fallen way off. And this other includes things like biomass and geothermal, so pretty flat there as well. But this is some of the exciting news. This is the percentage of new capacity installed in a given year. And going back to 2014, or actually let's go back to 2012, 4 of the last 5 years, the majority of new capacity has been wind and solar. So that's a big deal. And here's the Colorado, going back to 1996. This is the Colorado mix of electricity generation, the same general trend. You see, going back here to the early 2000s, we were all coal and natural gas and hydro, the gray, this teal, and the blue. And then this different shade blue starts coming on here around 2004. That's wind. And then solar starting to make its appearance here in 2010 and out to here. So still a small fraction, but with the current market conditions, things are changing very quickly. And you can see the downturn in coal and the increase in gas and wind and solar. So this is, I'll skip this for now, but this is, we've done the most detailed model at NREL of the eastern interconnection in the U.S. that's ever been done. We modeled the operation of the entire eastern interconnection on 5-minute intervals, 7,500 generators. This represents the scenario we did was 30% of the annual energy was supplied by wind and solar in the entire eastern U.S. So we modeled 7,500 generators. We had data for the loads at 60,000 transmission substations in the eastern U.S. It's an enormous system. And so we wanted to ask the question, can you operate this system with 30% wind and solar? It's much more challenging because utilities are used to variability and uncertainty in the load. It changes throughout the day. They have a good idea of how it's going to change, but they don't know exactly, so there's some uncertainty. Wind and solar introduce variability and uncertainty into the supply, and that's something they're not used to, and this presents very real challenges for them. So we work with them to try to do these scenarios to see what the challenges are, where we can find flexibility in the system, without having to buy storage, and it turns out there's a lot of it. And we ended up answering, yes, you can operate the eastern interconnection with 30% wind and solar. We're only at about 6 or 7% right now, so we've got a lot of headroom before storage is really needed. But we need to work on storage now because when we do need it, we can't start then, right? So just a couple of closing slides about jobs. This is U.S. electricity generation jobs. Look at solar. 15 is the dark bar, 16 is the light bar. More jobs in solar than nearly everything else combined. A lot of jobs in wind. But you see out here, and again, this is only the generation portion, doesn't go through the fuel, doesn't account for the fuel part, the mining and drilling, the extraction industries, but they're not large numbers either. I mean, these are good paying, very plentiful jobs that are coming with this market boom. And then lastly, for Colorado specifically, this 2016 numbers, 8,000 jobs total in solar, 7,000 in wind. And you can see the others here. Natural gas generation, 486 people. Coal generation, 3,800 people. Again, not including the extraction portion of the fossils. So these are total jobs. So these numbers add up to this 25,000 number. And the extraction part of the industry is another 36,000 jobs. Transmission, distribution, and storage, 28, and efficiency, nearly 30,000 jobs. So efficiency and renewables really are very solid employers in the state. So yeah, it's hopefully I've conveyed it, but it's a darn exciting time in renewables. One that I wasn't sure I would see in my career, but it's definitely happening, and it's been very exciting to be a part of it. And thank you all for all you do and your interest, and it's been really a great pleasure and honor to come up and talk. I do believe very strongly in the laboratory and the role that it's played in what I hopefully demonstrated tonight. I mean, we're certainly not the only players. There are many private sector companies and investors, but working all together, we're transforming the system. We have set the system now, I think, on a course to be a clean electricity system, and NREL has played, I think, a significant role in that. The study that you talked about, all the federal labs in Colorado stimulate the economy to the tune of about $2.6 billion, the Colorado economy. That's NREL and NOAA and NCAR and some other smaller labs. NREL specifically, there's been a separate study done on NREL's economic impact, and it's about $850 million to the state. So that's not insignificant. But what I would like to say on behalf of NREL is it's been such a great honor for me to be associated with the lab, mostly because of the quality of the people there, the commitment. We do have colleagues leave and they go and they say, I got this offer, they're giving me 50% more money, and I just couldn't pass it up, and that's totally understandable. And we like that. We like people who got trained up at NREL to go out and practice what they've learned. But most of us are there because of commitment to the mission, and that's made a big difference and been a great part of my career.
40 years.
40 years this year, yeah, 40 year anniversary, yeah.